Good day, class. I'm Nariza Tibonsadi from the Institute of Civil Engineering, and I will be your lecturer for the first three modules of ES 102, the Mechanics of Deformable Bodies. Today we will discuss Module 1, which is a lecture on internal forces. By the end of this lecture, you should be able to differentiate and explain external forces and internal forces with respect to members forming a structure. State the three types of internal forces that can appear in a member acted upon by a general coplanar force system. State the six types of internal forces that can appear in a member acted upon by a general force system. And finally, determine the internal forces at any section of a given member. Now, if you're ready, let's now move on to the lecture proper. Since you are in engineering, you will encounter designing structural or mechanical members. And to design these members, it is necessary for you to know the loading acting within the member in order to be sure the material can resist this loading. So there is a need to determine not only the external forces acting on the structure, but also the forces which hold together the various parts of the structure. These forces are called the internal forces. Internal forces are forces and moments that are developed in between particles inside a body because of the application of external forces. Let us first consider a straight two-force member as shown in Figure 1. A two-force member is a body that has forces and only forces, no moments, acting on it in only two locations. In order to have a two-force member in static equilibrium, the net force at each location must be equal, opposite, and collinear. So therefore, to satisfy equilibrium, we know that the forces F and negative F, both vectors, acting at A and B respectively, must be directed along AB in opposite sense and must have the same magnitude F. Now let us cut the member at C. To maintain the equilibrium of the free bodies AC and CB, in Figure 2, you must apply to AC a force vector of negative F equal and opposite to the force vector F at A. And to CB, a force vector F equal and opposite to the force vector negative F. These new forces are directed along AB in opposite sense and have the same magnitude F. Note that internal forces equivalent to these new forces are present in the member itself even before the member AB was cut. To satisfy equilibrium, the sum of external and internal forces should be equal to 0. Also note that the common magnitude F of these forces is independent of the location of the section. So even if we transfer point C to a location near point B, we will still have the same magnitude of the internal force. Therefore, we can conclude that in the case of a straight two-force member, the internal forces that the two portions of the member exert on each other are equivalent to axial forces. So what is an axial force? An axial force is generally defined as the force acting along the axis of the member. It can produce either tension or compression. So in this example, the member is in tension and will elongate under the action of the internal forces. Internal loadings such as forces and moments can be determined using the method of sections. To illustrate this method, consider the cantilever beam in Figure 3. Recall in ES 101, you are required to determine the support reactions at A. Since this is a cantilever beam, we have three reactions at the fixed support. We have AX, AY, and MA. You can determine these reactions using the three equilibrium equations as discussed in ES 101. Going Going back in our discussion about internal loadings, if the internal loadings acting on the cross-section at point B are to be determined, we must pass an imaginary section AA perpendicular to the axis of the beam through point B and then separate the beam into two segments as shown in figure 4. The internal loadings acting at B will then be exposed and become external on the free body diagram of each segment. Note that in figure 4, the support reactions at A are also included in the free body diagram. The force component NB that acts perpendicular to the cross-section is termed the normal force. The force component VB that is tangent to the cross-section is called the shear force. And the couple moment MB is referred to as the bending moment. The force components prevent the relative translation between the two segments, and the couple moment prevents the relative rotation. According to Newton's third law, the internal forces must act in opposite directions on each segment. So as you can see, if the normal force in the left segment is directed to the right, then the normal force in the right segment should be directed to the left. Same as if the shear force is directed downwards in the left segment, then it should be directed upwards in the right segment. Also, if the bending moment is counterclockwise on the left segment, then it should be clockwise in the right segment. Note that Newton's third law, which is based on experimental evidence, is one of the 6 fundamental principles of elementary mechanics, and its application is essential to the solution of problems involving connected bodies. Now, the magnitude of these internal forces can be determined by applying the equations of equilibrium to the free body diagram of either segment. In this case, however, the right segment is the better choice since it does not involve the unknown support reactions at A. So we can solve for the internal loadings at B even without solving the support reactions at A if we are to consider the right segment. A direct solution for the normal force at B is obtained by applying summation of forces about the x-axis equal to 0. The shear force at B is obtained from summation of forces y equal to 0. And the bending moment can be obtained by applying the summation of moments about point B equal to 0, since the moments of the normal force and the shear force about B are 0. In 2 dimensions, we have shown that if we use the method of sections, 3 internal loading resultants exist: the normal force, the shear force, and the bending moment as shown in figure 6. To determine the internal loadings, the 3 equilibrium equations, the summation of forces about the x-axis equal to 0, the summation of forces about the y-axis equal to 0, and the summation of moments about point O equal to 0 are performed using the sectioned member in figure 6. For the summation of fx, we have the x component of F1 plus the x component of F2 plus the normal force and then equate it to 0. Therefore, if F1 and F2 are given, the normal force N is equal to the negative of the summation of F1x and F2x. Now, for the summation of Fy, we have the y component of F1 plus the y component of F2 plus the shear force and then equate it to 0. Therefore, the shear force V is the negative of the summation of F1y and F2y. for the summation of moments about O, we have the position vector r1 cross the force vector f1 plus the position vector r2 cross the force vector f2 plus the bending moment at O, and then equate it to 0. The bending moment at O is therefore equal to the negative of the summation of the moments due to F1 and F2. Engineers generally use a sign convention to report the three internal loadings N, V, and M. Although this sign convention can be arbitrarily assigned, the one that is widely accepted will be used here. The normal force is said to be positive if it creates tension. Imagine that we fix this segment on this side. This segment will be under tension. Same as if we fix this side, this other segment will also be under tension. Therefore, the normal force in both of these segments are said to be positive. A positive shear force will cause the beam segment on which it acts to rotate clockwise. So if we fix this side of the segment, the shear force going downward will cause the segment to rotate clockwise. Same as if we fix this side of the segment, the shear force going upward will also cause the segment to rotate clockwise. Now looking at this third scenario for the shear force, obviously these two shear forces will cause the segment to rotate clockwise. Therefore, the shear force in these three scenarios are said to be positive. A positive bending moment will tend to bend the segment on which it acts in a concave upward manner. So if you fix this side of the segment, the bending moment will tend to bend the segment in a concave upward manner. Same as if we fix this side of the segment, the bending moment will also tend to bend the segment in a concave upward manner. Now looking at this third scenario, for the bending moment, obviously these two bending moments will cause the segment to bend in a concave upward manner. Therefore, the bending moment in these three scenarios are said to be positive. Loadings that are opposite to this are considered negative. In 3 dimensions, a general internal force and coupled moment resultant will act at the section. The XYZ components of these loadings are shown in figure 7. Here, Ny is the normal force since it acts perpendicular to the cross section. And Vx and Vz are shear force components since they act parallel to the cross section. My is a torsional or twisting moment since it causes the member to rotate along its axis. And Mx and Mz are bending moment components since they cause the member to bend. For most applications, these resultant loadings will act at the geometric center or centroid C of the section's cross-sectional area. Although the magnitude for each loading generally will be different at various points along the axis of the member, the method of sections can always be used to determine their values. For the sign convention, if the member is subjected to a three-dimensional external loading, then the internal loadings are usually expressed as positive or negative, in accordance with an established XYZ coordinate system such as shown in figure 7. So for 3D, again, follow the sign convention in figure 7. Or recall the right-hand rule in determining the positive axis. In the right-hand rule, you use your thumb to point to the positive x-axis, your index finger to point to the positive y-axis, and your middle finger to point to the positive z-axis. Also, you can use the right-hand rule to determine the vector direction of moments. If you grip the imaginary axis of rotation of the rotational force so that your fingers point in the direction of the force, then the extended thumb points in the direction of the moment vector. Similarly, to determine the direction of rotation about an axis, for example the z-axis, we use our right-hand thumb and point it upwards towards the z-axis and obtain the direction where our fingers curl. That is the direction of the rotation. Recall that two force bodies are bodies that are acted upon by forces at 2 points only. These forces have the same line of action, same magnitude, and opposite direction. Considering first a straight two-force member AB, we recall that such a member is subjected at A and B to equal and opposite forces F and negative F directed along AB. Cutting member AB at C and drawing the free body diagram of portion AC, we conclude that the internal forces which existed at C in member AB are equivalent to an axial force negative F equal and opposite to F. We note that in the case of a two-force member which is not straight, the middle figure and the rightmost figure, the internal forces are reduced to a force-coupled system and not to a single force. So the internal forces in two-force members which are not straight are normal, shear, and moment. Consider, for example, the crane shown in Figure 8, which carries a load W. The crane consists of 3 beams AD, CF, and BE connected by frictionless pins. It is supported by a pin at A and by a cable DG. The free body diagram of the crane is shown in Figure 9. The external forces which are shown in the diagram include the weight W, the two components AX and AY of the reaction at A, and the force T exerted by the cable at D. Note that cables are flexible members capable of withstanding only tension. They are designed to support either concentrated or distributed loads. They are used in many engineering applications such as suspension bridges and transmission lines. So the direction of force T exerted by the cable, since it can only withstand tension, is always away from the member considered in the FBD. The internal forces holding the various parts of the crane together do not appear in the diagram or Figure 9. If, however, the crane is dismembered, and if a free body diagram is drawn for each of its components, or for each of its component parts, the forces holding the 3 beams together will also be represented, since these forces are external forces from the point of view of each component. Note that in Figure 10, the force exerted at B by member BE on member AD has been represented as equal and opposite to the force exerted at the same point by member AD on member BE. The force exerted at E by BE on member CF is shown equal and opposite to the force exerted by CF on BE. And the components of the force exerted at C by CF on AD are shown equal and opposite to the components of the force exerted by AD on CF. This is in conformity with Newton's third law, which states that the forces of action and reaction between bodies in contact have the same magnitude, same line of action, and opposite sense. The two force members should also be considered. In this frame, member BE is the only two force member. The forces acting at each end of this member must have the same magnitude, same line of action, and opposite sense. So since this is a straight two force member, the internal force can produce only tension or compression in this member. The direction of the internal forces in member BE are also reflected in members AD and CF as shown in the previous slide. Next, let us consider a multi-force member. Take for instance member AD in figure 12. We now cut member AD at an imaginary section J and draw a free body diagram for each of the portions JD and AJ of the member. Considering the free body JD, we find that its equilibrium will be maintained if we apply at J a force F to balance the vertical component of T. Also a force V to balance the horizontal component of T. And the couple M to balance the moment of T about J. The internal forces acting on the portion JD of member AD are equivalent to the force couple system shown in figure 13. According to Newton's third law, the internal forces acting on AJ must be equivalent to that in JD but with opposite directions as shown in figure 14. It is clear that the action of the internal forces in member AD is not limited to producing tension or compression as in the case of a straight two-force member. The internal forces also produce shear and bending. The force F here is an axial force. The force V is called a shearing force. And the moment M of the couple is known as the bending moment at J. We note that when determining internal forces in a member, we should clearly indicate on which portion of the member the forces are supposed to act. In summary, the method of sections can be used to determine the internal loadings on the cross-section of a member using the following procedure. So before the member is sectioned, it may first be necessary to draw the external FBD and determine its support reaction. So for number 1, we draw external FBDs showing the external forces and reactions. And number 2, we determine the unknown external forces and reactions, if any, using equilibrium. Number 3, keep all distributed loadings, couple moments, and forces acting on the member in their exact locations. Then pass an imaginary section through the member perpendicular to its axis at the point where the internal loadings are to be determined. After the section is made, draw a free body diagram of the segment that has the least number of loads on it, and indicate the components of the internal force and couple moment resultants at the cross-section acting in their positive directions to the established sign convention. Number 4, determine the unknown internal forces using equilibrium. Moments should be summed at the section. This way, the normal and shear forces at the section are eliminated, and we can obtain a direct solution for the moment. Note that if the solution of the equilibrium equations yield a negative scalar, the sense of the quantity is opposite to that shown on the free body diagram. Now let's discuss some examples. So for example number 1, the 500 kilogram engine is suspended from the crane boom as shown. Joints A, C, and D are connected using frictionless pins. Determine the internal force or forces and moments acting on the cross-section of the boom at point E. Following the steps for analysis, we first draw the external FBDs showing external forces and reactions. So in this example, it is helpful to dismember the crane. FBD is drawn for each of its component parts, therefore showing the external forces from the point of view of each component part. So first, we have bar CD. It should be noted that by inspection, member CD is a straight two-force body. Next, we have bar ACB. Shown in the FBD are the support reactions at A, the weight of the engine, and the force due to bar CD. So in drawing the forces, always follow Newton's third law. We now determine the external forces and reactions by considering member ACB using equilibrium equations. We will follow the sign convention in ES 101 for the summation of external forces and moments. So for the x-axis, positive if going to the right. For the y-axis, positive if going upwards. And for the moments, positive if counterclockwise. First, we sum moments about point A. We have the vertical component of FCD, that is FCD multiplied by 3/5 multiplied by the perpendicular distance of 2 meters. So this term is positive since it causes a counterclockwise rotation at A. Next, we have the weight of the engine multiplied by the perpendicular distance of 3 meters. So this next term is negative since it causes a clockwise rotation at A. And then, we equate the summation of moments to 0 and determine the unknown force FCD. So FCD is equal to 12,262.5 newtons. Next, we sum forces about the x-axis. We have AX, positive since AX is to the right, and the horizontal component of FCD, which is FCD multiplied by 4/5. This is negative since the horizontal component of FCD is to the left. We equate the summation of forces to 0 and determine the unknown force AX. So since FCD is given in the previous equation, so FCD is equal to 12,262.5 newtons, we now have our AX equal to 9,810 newtons. Next is summing forces about the y-axis. So we have AY, that is negative because it's going down. And then we have the vertical component of FCD, that is FCD multiplied by 3/5. This term is positive since it is going up. And the weight of the engine, that is 500 multiplied by 9.81, negative since going down. And then we equate the summation of forces to 0 and determine the unknown force AY. So again, since FCD is given, we have AY equal to 2,452.5 newtons. Next is to draw a sectional FBD of the segment chosen. So this is done by passing an imaginary section through the member, perpendicular to its axis at the point where the internal loadings are to be determined. So in this example, segment AE is chosen. The free body diagram of segment AE is shown in the figure. As you can see, the internal forces are now exposed. We assume the positive direction of the internal loadings as discussed in the previous slides. So for the normal force in member AE, we assume that the member is in tension. For the shear force, we use a downward direction to create a clockwise rotation. And for the bending moment, we use a counterclockwise direction to create a concave upward bending. Using equilibrium equations, we can now determine the internal forces and moment acting on the cross-section of the boom at point E. Again, using equilibrium equations, we follow the sign convention in ES 101. Positive if going to the right, positive if upwards, positive if counterclockwise. First, we have summation of moments about point E equal to 0. So we have ME. ME is positive since it is counterclockwise. And then we have AY, that is 2,452.5 newtons multiplied by the perpendicular distance 1 meter. This term is also positive since it creates a counterclockwise moment about point E. Then equate it to 0. ME is now equal to negative 2,452.5 Newton meters. So since the solution of ME yielded a negative scalar, the sense of this quantity is opposite to that shown on the free body diagram. So therefore, ME should be 2,452.5 Newton meters clockwise instead of counterclockwise. Next is we sum forces about the x-axis equal to 0. So in the x-axis, we have the normal force, NE, positive since going to the right. And then we have another force that is the 9,810 newtons. Again, positive since going to the right, and then equate it to 0. From this, NE is now equal to negative 9,810 Newton. So again, since the solution of NE yielded a negative scalar, the sense of this quantity is opposite to that shown on the free body diagram. So therefore, NE is equal to 9,810 newtons to the left. And then lastly, we have summation of forces about the y-axis equal to 0. So we have VE, or the shear force at E, point E, that is negative since it is going downwards. We also have the 2,452.5 Newton force at point A. Again, it is negative since it is going down again. Again, equate it to 0. Now we have VE equal to negative 2,452.5 newtons. So since it is negative again, negative scalar, the sense of this quantity is opposite to that shown on the free body diagram. So VE is now equal to 2,452.5 newtons going upwards instead of downwards. Okay. So we have a question here. What if we use segment ECB? What changes? So of course, when we use member ECB, note that the shear, the normal force, and the bending moment will have the opposite direction as in the FBD here in segment AE. Let's move on to another example. We have end A of the pipe shown is subjected to a vertical force of 15 newtons, a horizontal force of 30 newtons, and a couple moment of 70 newton meter, while end C is attached to a fixed support. Neglecting the pipe's mass, determine the resultant internal forces and moments acting on the cross-section at point B. So this problem can be solved by considering segment AB. So we do not need to calculate the support reactions at C. By cutting the pipe at an imaginary section B and drawing the FBD for segment AB, the resultant internal forces and moments are shown. The XYZ axes are established at B. The resultant force and moment components at the section are assumed to act in the positive coordinate directions and to pass through the centroid of the cross-sectional area at B. So recall the sign convention that we have established earlier in our discussion. By applying the 6 scalar equations of equilibrium, we can now directly determine the resultant internal forces and moments at point B. So let's start with summation of Fx equal to 0. So looking at the forces about the x-axis, we only have Fbx. So Fbx is equal to 0. Next is we sum forces about the y-axis, then equate it to 0. As you can see, forces about the y-axis are Fby and the 30 newtons. Both are directed in the positive y direction. So we have Fby plus 30 equal to 0. So if we want to get Fby, we transfer the 30 to the right-hand side of the equation. We have Fby equal to 30 newtons. Actually, it's negative 30 newtons. Since it is negative, so the direction should be negative the y-axis. So instead of going to the positive y-axis, the direction is opposite. Next is summation of forces about the z-axis equal to 0. So in summation of forces about the z-axis, we only have FBZ positive since it is going up or going to the positive z direction. And then we have the 50 newtons at point A going downward, so negative since going to the negative z direction, and then equate it to 0. So therefore, we have FBZ equal to 50 newtons. So since positive, the direction is going upwards or in the positive z direction. Next is with some moments about the x-axis at point B and then equate it to 0. So we have MBX positive since it is directed in the positive x-axis. And then we have the 70 Newton meters, again positive because it is directed to the positive x-axis. And then we have another force which is the 50 newtons, which creates again a moment about the x-axis. However, the rotation is towards the negative x-axis. So we have negative 50 multiplied by the perpendicular distance of 0.5 meters equal to 0. Therefore, we have MBX equal to negative 45 Newton meters. So since it is a negative scalar, the direction of MBX should be directed to the negative x-axis. Next is with some moments about the y-axis, then equate it to 0. So we have MBY positive since it is going to the positive y direction. And then again, we have the 50 newtons. 50 newtons create again a moment about the y-axis using the perpendicular distance of 1.25 meters. So as you can see, the rotation that it creates is pointed towards the positive y-axis, so it is positive. And then equate it to 0. We therefore have MBY equal to negative 62.5 Newton meters. Since it is negative scalar, the direction of MBY is in the opposite direction. So instead of going to the positive y-axis, it is directed to the negative y-axis. Next is summing moments about the z-axis at point B, then equating it to 0. We have MBZ positive since it is pointing towards the positive z-axis. And then we have the 30 Newton force with its perpendicular distance of 1.25 meters, which creates a moment about the z-axis. So the moment it creates is pointed towards the positive z-axis. So the term should be positive. And then equate it to 0. We therefore have MBZ equal to negative 37.5 Newton meters. Since again it is negative scalar, so the direction of our moment at point B about the z-axis is directed in the negative z-axis. Something to think about. Can we use vectors in determining the resultant internal moments? So the answer is yes. We can use vectors to solve for the resultant internal moments. So given in this slide is the vector solution for the internal moments. Recall the discussion in ES 101. To determine the moments at point B about X, Y, and Z. So as you can see, the answers here are the same as the answers in the previous slide. For last example, example number 3, the structure shown is composed of members ABE, BCD, and ACF. They are connected by frictionless pins at A, B, and C. The structure is supported by a pin at E and a roller at F. Determine the internal forces developed in member ACF at section J due to the 2,400 Newton vertical load. Following the steps for analysis, we first draw the external FBDs showing external forces and reactions. So as you can see, since E is supported by a pin, we have two force components, EX and EY. While F, since F is supported by a roller, we only have one support reaction, that is a vertical component of F. The reactions EX, EY, and F are then determined using the equilibrium equations, summation of moments about point E equal to 0, summation of forces about the x-axis equal to 0, and summation of forces about the y-axis equal to 0. Let's start with summation of moments about point E equal to 0. So we have force F multiplied by the perpendicular distance, 4.8 meters, positive since it is producing a counterclockwise moment. And then we have the 2,400 Newton force multiplied by the perpendicular distance of 3.6 meters, negative since it produces a clockwise moment, and then equate it to 0. Therefore, F is equal to 1,800 newtons, a positive scalar, therefore going up. Next is we sum forces about the x-axis and then equate it to 0. We only have one force about the x-axis, that is EX. So therefore, EX is equal to 0. And last but not the least, we have summation of forces about the y-axis equal to 0. So in this, we have EY and F and the 2,400 newtons going downward. So we have EY positive since going upwards, F positive since going upwards, and then 2,400 which is negative since going downwards. Then equate it to 0. So given the value of F, we substitute in this equation, we have EY equal to 600 newtons going up. Going up since the direction or the scalar quantity is positive. So we retain the original direction. Next is to dismember the frame. FBD is drawn for each of its members, therefore showing the external forces from the point of view of each component part. The reactions and the forces acting on each member of the frame are determined using the equations of equilibrium, as will be shown in this slide. So first, we have member BCD. So as you can see in the free body diagram, the internal loadings are now exposed. First, we sum moments about point B, then equate it to 0. So we have cy multiplied by the perpendicular distance of 2.4, positive since it creates a counterclockwise moment. And then we have the 2,400 Newton load multiplied by the perpendicular distance of 3.6 meters, negative since it creates a clockwise moment, then equated to 0. From here, we have cy equal to positive 3,600 newtons. So, since this is a positive scalar, the direction is retained. So, cy is upwards. Next is we have member ACF, but before that, if we want to determine by in member BCD, we can use summation of forces about the y-axis to determine the reaction at B, which is yung BY. So moving on to member ACF, we can sum moments about point A and then equate it to 0. So summing moments about point A, we have cy multiplied by the perpendicular distance. The perpendicular distance is 4.8 minus 2.4 meters. Then it creates a clockwise moment, so therefore that is negative. And then we have cx. Cx has the perpendicular distance to A of 2.7 meters. Again, it creates a clockwise moment, so negative about point A. Then last but not the least, we have 1,800 Newton force at point F multiplied by the perpendicular distance of 4.8 meters. So it creates a counterclockwise moment, so therefore that is positive, and then equate it to 0. The answer for Cx is therefore equal to 0. Cy is given in the previous calculation. So Cy is equal to 3,600 newtons. Using the values in the previous calculations, we have Cx is equal to 0. And then we have summation forces about the x-axis equal to 0. So we have Cx, we have Ax, two forces. So therefore, we have positive Ax minus Cx, wherein Cx is equal to 0, and then equate it to 0. So therefore, Ax is also equal to 0. And then last but not the least, we have summation of forces about the y-axis and then equate it to 0. So for this, we have Ay, Cy, and the 1,800 Newton force. Cy is given 3,600 newtons going upward. Ay is unknown. Then we are given 1,800 newtons. So therefore, Ay is equal to 1,800 newtons going up. Next is we consider member ACF. To determine the internal forces at J, member ACF is cut at point J. In the two parts, segments AJ and JF are obtained. The internal forces at J are represented by an equivalent force couple system. So we have a normal force F, a shear force V, and a bending moment M. And this can be determined by considering the equilibrium of either part. Considering segment AJ, the axial force F, the shear force V, and the bending moment M are determined by applying the equilibrium equations. So we have summation of moments about point J equal to 0. We have bending moment. The bending moment is positive in direction because it is counterclockwise. And then we have the 1,800 Newton force multiplied by the perpendicular distance of 1.2 meters. The direction is clockwise, so therefore the sign is negative, and then equate it to 0. We therefore have the bending moment equivalent to 2,160 Newton meter. This is a positive scalar, so therefore the direction is retained. Next, we have summation of forces about the x-axis equal to 0. So we have force F directed to the positive x-axis, and then we have the 1,800 Newton force. The component of this in the x-axis is negative because it is directed to the negative x-axis. So that is negative 1,800 cosine alpha. Alpha is equivalent to 41.7 degrees. And then equate it again to 0. We therefore have F equal to 1,345.34 newtons. Positive scalar, so therefore the direction is retained. Last but not the least, we have summation of forces about the y-axis equal to 0. We have V directed to the negative y-axis, so the term is negative. And then we have the y component of the 1,800 Newton force. So that is 1,800 multiplied by sine alpha. Again, alpha is 41.7 degrees. This term is positive since the y component is directed to the positive y direction. Then equate it to 0. We therefore have V equal to 1,195.85 newtons. Again, positive scalar, so therefore we retain the direction of V. So for your practice, write the solution for the given problem. The answers are already provided for your reference. These are the content references and the image references. And that's it. That's the end of Module 1. I hope you've learned a lot today, and hopefully you'll practice this on your own. Thank you for listening.